All right, this is the start of Chapter 18, Refraction and Lenses. Today we're going to talk about refraction of light. If I remember correctly, we're not going to talk about ray diagrams today. We're just going to talk about the setup of this index of refraction and what refraction is. So we'll calculate index of refraction. We'll calculate the speed of light through medium. We'll calculate the angle of refraction and talk about the critical angle and how fiber optic cables work. So refraction. It happens whenever light crosses a boundary. So from air into glass, from air into water, from water into glass. Whenever it changes the medium that it's in, it's going to bend. And this how much it's bent is depend mostly on the density of it. And that density sort of idea is called the index of refraction. The denser the medium, the higher the index of refraction. Your index of refraction is always going to be 1 or bigger, since our index of refraction for a vacuum is 1, and air is pretty close to 1. You can assume that air is 1 if you want to in your calculations. That's fine. But as we get denser and denser materials here, you can see that the index of refraction climbs all the way up to diamond. And that's 2.42. Yes. Yeah, in Chapter 18, there'll be a book. It's also in the back of your book, I think, too. Each substance has its own special index of refraction. How many of you have mowed the lawn and went from the grass and then one of the tires went onto the sidewalk, and it's like bent, and it's like goes everywhere? Same idea. Same idea. So when you change that medium, it causes it to move differently. So when it changes, it's going to bend or change its path. So it does this. Actually, there's a good picture right here on the very front. You can see right here, when it goes from air to water, that it's cut in half. And then when we have like oil and water going on here, it's cut in half and then cut again. You actually see it's moved. And then here, same idea. But you notice that it's further when it goes through the oil than it does when it's going through whatever these clear liquids are. A little bit different. So that's just because when the light rays go, they bend differently for your eye, so they look like they're starting in a different spot, even though we know that there's nothing broken about the little straw that's in there. So here's how to calculate the index of refraction. It's a ratio of velocity, where c is the speed of light, and v is the speed through the medium that you're in. So if you're going through a vacuum, the speed of light is 3 times 10 to the 8, so you end up with 3 times 10 to the 8 over 3 times 10 to the 8. So a vacuum is 1. And nothing can go faster than the speed of light, so your index of refraction should always be bigger than 1. And the more dense or the higher the index is, the slower the light is going to move. This might be why diamonds are so sparkly, because the index of refraction is really high. It's 2.42. It's the highest that I know it's naturally the highest. I don't know if there's any unnatural materials that we've made that actually have a higher index. But that could be the sparkliness of your diamonds. Since the index of refraction is ratios, it has no units. Think about walking versus trying to walk in water. It's harder, right? There's more resistance, same idea. All right. When light moves from a less dense medium to a more dense medium, it is going to refract towards the normal. Remember with reflection, we were talking about how to measure towards the normal. So here's our surface. And when we have an incident ray, which is our initial ray, we always measure this angle. This is our incident angle or initial angle. That helps you remember. The refracted ray, well, let's draw the reflected ray first since we know what the reflected ray is. The reflected ray is the same thing as the incident angle. So this is what we learned with mirrors, reflected. And with glass, some of it is reflected. But most of the time with glass, we can see through it as well as see as our reflection. So refraction is talking about the light that's passing through the glass. So our refracted ray, or transmitted ray, if you want, is going to be this angle. And this is refracted, but I can't use an R, so I'm going to use a T for transmitted. So it's measured towards the normal. It's on the opposite side of the surface, the surface of our object, our boundary. And it is also measured to the normal. Now this would be from a less dense medium to a more dense medium. If we were going to do the opposites, this would be like from air to water. Because air is 1 and water is 1.33. But let's say that we're going from water to air. So our light ray comes in, and now it's going from a more dense medium to a less dense medium. So our refracted ray is actually going to get bigger. So skinnier when it goes into more dense and bigger when it goes into less dense. What's interesting about this, if you look at the little picture that I have in my PowerPoint up here, if we have this angle is going to match the refracted angle over here because this is air and this is air. So that's kind of neat that it does that. So it goes into the glass, it bends, but then when it comes back out of the glass, it goes back to the way it was before it went in. Now, how do we calculate these angles? We're going to use Snell's law. That's Snell, not snail. So we have N1 sine theta 1. This would be like your first surface. So if you're talking about air, it's the angle that's going from the air to whatever your boundary is, and the index of refraction of air, which we'll just use 1, because it's like 1.0003. And then on the other side, we have N2 sine theta 2. This would be like, if it's going from air to glass, this would be everything that has to do with the glass. The index of refraction of glass and the refracted angle that's happening in the glass. You need to make sure that your angles are in degrees and your calculator is in degrees. So if you're in pre-calc or calc, and you've got that thing in radians, you make sure you turn it back to degrees. And maybe buy another calculator for this class. Again, remember that the index of refraction has no units, so the only units going into this are degrees. And always measure to the normal. Don't ever measure to the surface. This will not give you the right answer. All right, rainbows. Since we're talking about refraction, let's talk about prisms. If we take white light and we send it through a prism, so I got my little prism right here. It's kind of fancy. The light hits this angled surface, and since each of the colors in white light is a different wavelength, this angled surface causes it to spread out even more until we can see the different red, green, blue light. And so you get this beautiful rainbow. Now this little prism here will split light, but I need a powerful light source. This little flashlight right here, not really that powerful. I can get kind of like a little tiny one. Where is it here? There it is. But you can't really see it very well, and it's because the beam is not strong enough and it's super wide. So if you want to see a real rainbow with this prism, you could take it outside. Right? The sunlight from outside is very powerful. Very strong. Mag lights, you can kind of see a little bit of rainbow there, but I don't mind any colors. So maybe not. All right. Way back when they first started working with prisms, there were some scientists that thought that maybe the prism, the glass itself, held the light. And so you shine white light, it would just shine that color light like stained glass produces a color. And so some people were thinking maybe it's just the glass itself that has the color in it. They were able to disprove that theory by using two prisms. If it came from the glass, it wouldn't matter what color light went in. That color light is still going to come out because it's within the glass. So if we put another prism right here, and it was the prism producing the light, let's see, it would have to be like that. I don't know, that at least. So if it was the prism producing the light and not the light itself, then it would still be a rainbow. But this one broke it apart, and when they put the second one in, put it back together so white light came out. So they were able to say, okay, it's actually a property of the light. We can separate it, and we can add it back together, which is pretty neat. I want to say they did that back in the 14 or 1600s. I'm really bad with dates, I'm not sure. But it was a long time ago. All right, rainbows work the same way. I think these are some very pretty pictures. I think that's why I put it in here. So we have our incident light ray, our sunlight comes in and it hits the water droplet. Now the water droplet is spherical, so when it hits, it has this angle to it. And since, again, each of the different colors of light have different waves, have different wavelengths, these wavelengths are going to get separated and they spread out. Once they spread out, they get reflected off the back of the raindrop a couple of times and then come out and spread out. So we end up seeing our rainbow on these different types of raindrops. And depending on where you're located, you're going to see that color based on your location. So you're never going to see red on the top of rainbow. It's always going to be on the bottom of rainbow for this reason. Because it's got a larger wavelength, so it has a less angle of refraction. Didn't help. Okay, total internal reflection. I'll let you look at this slide a little bit before I talk about it. Now with total internal reflection, we have our surface, let's say that this is a piece of glass or like a fiber optic cable. Now, sometimes when you hit this piece of glass from the inside, which is a little weird, but if our light source, if this is glass and this is, let's call it air out here, if we hit our piece of glass from the inside at the critical angle, which is the angle that causes it when it refracts, instead of refracting up here, it actually refracts along the outside edge. And this is called the critical angle. So when the incident angle is equal to the critical angle, you get this 90 degrees of refraction. And so the light source is able to, or the light is able to travel along the outside edge of that cable for a while. What's neat about this is because our angle of reflection is the same as the angle of incidence, this will also be the critical angle. And geometry says that if you have a transverse across two parallels, so this is the normal, this is also going to be the critical angle. So it's going to refract along the outside edge and reflect at the critical angle. So you get this reflecting over and over and over again, and you can carry a signal at the speed of light. So that's what that Google fiber is that they're talking about laying in. I don't know if they're doing it around here, but I've heard of it before. Yeah.
What is a 90 degree angle?
The refracted angle. Yeah, that one that's going through. Instead of it coming out, it goes along the edge. And I can show you this with my little fancy flashlight here. Here it is. All right, so this is reflected over and over and over, and you can see it come out here. Here's my flashlight. I can also do it with laser light. Yeah. So the light is reflected over and over and over at this critical angle all the way through this, whatever it is. I think it's fiberglass, some sort of acrylic. So I'm going to pass this around. You guys can play with it.
Can that work the other way? Like
From here? I don't know. I've never tried it.
Where's it called?
Okay, so one of these is a laser. Please don't shine at anyone's eye. What is that? Pass it down. So to find this angle, since this angle that it's refracted at, if we look at Snell's law, let me look at Snell's law here. N1 sine theta 1 equals N2 sine theta 2. So if this is a critical angle, and this angle is going to refract at 90 degrees, this whole thing drops out to 1. So our critical angle, sine N2 over N1. Now you're only going to get a critical angle if you go from a more dense to a less dense medium. So it's only going to work from glass to air. It's never going to happen from air to glass. So this is not going to create it. So when you put the numbers in here and you get error, like ERROR, like your calculator won't do the calculation, it's possible that either you have them flip-flopped or that it's going from a less dense to a more dense medium and there is no critical angle. You can't do it. It doesn't work. So make sure you write this equation down and pay attention to, is it going from more dense to less or less dense to more?
Yeah, I'm back.
Well, you're still writing.
Again, I read it, so I know what it says.
My computer has decided it doesn't want to click. Come on. Wait.
What's the speed of what?
3 times 10 degrees.
Only happens when it goes from orange to left-hand.
Yes. All right, here's a gross picture of an eye. I mean, I have to show you a gross picture of an ear. I have to show you a gross picture of an eye. So here's your eye. It's kind of gross. Here's a lens. This lens that the light shines through is what focuses and allows you to see. So if you have to wear glasses or contacts, it's because your eye is not shaped the way it's supposed to be. Or it's not shaped the way that your lens is shaped. They don't match up. So this gathers the light and focuses it to the back of your eye where you have rods and cones that collect red, green, and blue light. In 1% of the population, and I believe it's only in women, there is a genetic mutation where they can actually collect one more color light wavelength. Their rods and cones collect just a little bit more, so they actually see even more colors than we do, which is pretty neat. And I can tell you that laser eye surgery, they cut the cornea and pull it back, and then stick lasers in your eye and fix it. And then they put it back, but this never heals back. So you have to be really careful after you have laser eye surgery never to rub your eye because it will take the cornea and flip it up and damage your eye. So, if you ever considered getting laser eye surgery, just be aware of that. It's kind of gross. And don't touch your eye, yeah.
How can someone see like a different color than I just don't understand.
They just collect that other wavelength. So infrared and ultraviolet is just on the outside. They can see that where
So like how
it's
did they
invisible
express
to us.
that? Like how did people discover that they could see that?
I think it's the same way that people discover they're colorblind. They just talk to people and be like, well, this one's purple. Well, I can't see purple. So this person's like, well, what is this color? And nobody has a name for that color because it doesn't work. And they're like, no, it's different. And we're just like, it's gray. So if you talk to colorblind people, like I have someone in my third period, she can't see red or green. It just looks gray up here. So I have to make sure I write in blue. So I'm assuming that there are some grays that are actually colors to those people. But I'm not sure. You'd have to talk to someone that has it. They're very rare, though. Okay, so when you're nearsighted or farsighted, what has happened is that when your brain grew, is it called the occipital cavity? The ocular cavity? Something to do with an eye. There's a hole in your head, right? Where your eye grows. And your brain, depending on its genetic makeup, either grew, and this only works for, if you can't, you have to have glasses to see, is that the hole that your eye grew into was not perfectly circular. It was instead either elongated like this or like this. So depending on how your eye grew, and if it didn't grow into a nice perfect circular thing, it's going to change where that lens of your eye focuses. So this is what it should do. The lens should focus it right to the back of these nerves where the rods and cones are so that you can see a nice clear point of view. This is like your camera. For those of you that are not nearsighted or farsighted. Imagine your camera when it's unfocused and it's all blurry. That's what we see all the time. So, I believe that if you are nearsighted, your eye has grown like this. So it's actually kind of flattened out a little bit. And so when it's focused, it's too short. So when the light rays keep going, they're actually unfocused because they're not all lined up. So we need lenses that will correct it. And then for those of us that are farsighted, it's actually like this. It looks like it's squished, but it's actually just grown this way. So it's too short. So the light rays are actually focusing behind it. So they can only see stuff that's far away instead of short and close, like the nearsighted. So it's all about how their eye grew and where that focus point is. Tomorrow we'll start talking about lenses and how it will change the focus point depending on when you put the light through. Now I know these are hard to see, but this is actually a diverging lens, and this is a converging lens. And I think my glasses are converging lenses. So those would be for your nearsighted people. All right, a telescope. If you look at a telescope, and I'm just waiting for my computer to catch up to me. It doesn't want to.
Miss Phillips, when you shine the laser or red one through the bottom, the top looks like it's fuzzy. Why does it look like that? Like it looks like things are moving.
I'm not sure.
Like it looks like when you turn a TV, like the ring or something, how it's like all fuzzy and stuff, but it looks fine. It's fuzzy.
I mean, some of that is probably because it's passing through and it's losing. You know, it's not perfectly clear, so it's not getting as much. So I'm not sure. Okay, telescopes. Now telescopes have an objective lens that collects all the light. And the bigger the objective lens is, the more light that it can collect. So if your eye was bigger, you'd actually be able to collect more light so you could see further and you could see more dim objects. Well, you can see further because you can see more dim objects. And what it does, it takes this light and it focuses it all the way down into an eyepiece, which is very small. So it takes all that light and it crams it down into a small location so you can look at it. So it's like making your eye that much bigger. So that's why really, really, really big telescopes can collect all this very faint light. Like the Hubble. This is the Hubble Deep Field. I'm pretty sure they stared at this spot in space for 9 months. So these are very dim objects that we can't see. But it collected all the light that it possibly could, and it stacked it on top of each other until it was able to make a huge and a beautiful image. So we can't see it with our eye because our eye is so small and we're not looking at it for very long. Binoculars work the same way. Notice the binoculars, the lens isn't even that much bigger than your eye, but it's still collecting more. And then the eyepiece, there's two lenses because we're not looking at stuff that's like super duper far away like telescopes, so we need to focus it a little bit better. So these lenses allow us to focus. So we have two eyepiece lenses and a nice light collecting lens called the objective lens. But because this stuff is fairly close to us, not like, light years away, and it has color to it, when we look through a lens, it does this spherical aberration where the colors are spread out, just like a prism, right? So in your binoculars, it has these two prisms to try to take this light and refocus it so that we can actually see in color without it being all rainbowy when you look through it. So I don't know if you've ever looked through binoculars, but they still have that rainbow effect to them. And that's why. It's because these lenses, when it goes through high-powered lenses, each color of light, each wavelength is going to refract at a different angle, and that's going to make it spread out. So you have all these lenses inside this binoculars. So you want to make sure you don't drop them, because it'll break those lenses. All right, we're going to practice Snell's law here. My practice says, what is the angle of refraction for light that hits glass from air with an instant angle of 15 degrees? And the index of refraction for glass is 1.52. You can just bring it right over here. It's fine. Thank you. All right, let's look at our problem. Now, at first, I find it helpful to kind of draw these things, and then you can just start plugging them into the equation. So we have from air to glass, we have our normal. Our index of, or our angle of incidence is 15 degrees. Air is 1, and glass is 1.52. The question is, what is the angle of refraction? So we're looking for this angle. Let's look at Snell's law. N1 sine theta 1 equals N2 sine theta 2. So everything up here is 1, everything down here is 2. So we'll have 1 sine 15 equals 1.52 sine theta 2. This gives me 0.26. We're going to divide. You get 0.17. Now, some people get stuck here. It's sine inverse to solve, so sine inverse both sides. That'll knock this out. And we get 9.8 degrees gives us theta 2. Okay, you guys ready for your clicker questions? I think I have 5. Question 1. The speed of light in a diamond is 1.24 times 10 to the 8 meters per second. What is the index of refraction of a diamond? And my computer is still catching up, so you can't put the clickers in yet. There it goes. Okay, you should be able to answer now.
Panties or underwear?
No, I don't.
Panties or underwear? Panties? She didn't even say anything. She just nodded. Panties or underwear? Is this being recorded? Oh my god. Oh well. Maybe that's what she's doing.
Actually, I probably don't need to record. We can end it.
Okay, so it's going to be the